Okay, so by the way, can you see through all this? Maybe you can. Is this getting in the way? No? Okay. Okay, so today we are going to talk about intro to probability. Okay, so just the basics. And all right, so let's start. So let's start with some things that I'm sure you know about already. So let's say you flip a coin. What's the probability you see heads? 0.5, 1/2. Now, what if you flip a fair coin twice? What's the probability you see heads? 1/4. How about if you flip it 3 times? What's the probability you see at least 1 heads? At least 1 heads is 7/8. How about the probability you see exactly 1 heads? Okay, so let's see what we are doing to figure these probabilities out. So what we say is that if you flip a fair coin once, there are 2 outcomes, heads and tails, right? These are the 2 possible outcomes, and they are equally likely. Right? When we flip a coin 3 times, now what are the outcomes? Well, the outcomes are heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, and right? So there are exactly 8 such possibilities. Right? And then we say, okay, so what's the probability at least 1 heads? Well, there are 7 out of these 8 possibilities which are consistent with that. And then, so we say the probability is 7/8. If we say, what's the probability exactly 1 heads? Well, now there are only these 3 possibilities which are consistent with that, with what we are looking for. So the probability would be 3/8. Yeah? Okay, so let's look at another example before we... Okay, so what we're going to do is we're going to formally try to understand what probability is. What does it mean, to define the probability of an event? What are these objects? Because once we define them, it'll be easier to understand what probability is about. But before we understand the definition, it's good to look at some examples that you're already familiar with. So the definition won't come as so much of a surprise. So let's say we roll a 6-sided die. Right? What's the probability we see an even number? One half, right? Okay, good. So why is that? Well, because our sample space consists of 6 points. There are 6 possible outcomes, 1, 2, 3, 4, 5, 6. Exactly half of them are even, half of them are odd. So probability is 3/6, which is 1/2. Okay. But now let's say we roll 2 6-sided dice. And we want to know what's the probability. Okay, let's do something a little more interesting. We want to know, is it the case that the probability of getting a pair meaning 2 1s or 2 2s or 2 3s, 2 4s, right? We get the same outcome on both dice. equal to, greater than, less than the probability that the sum equal to 7. Right, so we roll the two dice, we get two numbers. We want to know, how do these two quantities compare? The probability that we get the same number twice, or the probability that the sum of the two numbers is 7. Right? Okay, again, there's one way of doing it, which is, let's figure out, so how many possibilities are there? Well, you could get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, so on, right? All the way to 6, 6. So how many possibilities are there? There are 36, right? So then we'd figure out how many give us a pair. How many pairs are there? Exactly 6. So this probability is 6 divided by 36. How many of them sum up to 7? Is it 6 or 12? Okay, so it's either 6 or 12. So we can eliminate one of these possibilities, so it's definitely not greater than. And now which one would it be? Yes.
Are the two dice distinguishable?
I'm sorry?
Are the two dice distinguishable?
Yes, yes. Everything in the classical world is distinguishable. Yes, because, yeah, so the question you asked, okay, so maybe we'll get into it later, but indistinguishability only happens at the quantum level, or when you're talking about non-physical objects like zeros and ones, right? So, yes? Okay. So here's we can sort of work it through. You can sort of write up the entire table and figure out what the 36 items are. Or you can sort of say, let me just do a slight change in point of view, right? Let me look at this problem from a slightly different viewpoint, right? Now, suppose that, okay, so you have two different dice, right? So this one comes up 4, that one comes up 2, okay? All right, so you roll them, they come up with two different numbers, and now suppose that you were to interpret this output differently. So whenever it came up 2, you interpret it as 4. When it comes up 1, you interpret it as, when it comes up 1, you interpret it as 6. When it comes up 2, you interpret it as 5. Right? So you go, if it comes up 1, you call that 6. If it comes up 2, you call it 5. 3, you call it 4. 4, you call it 3, and so on. Okay, so now, suppose you were to get a pair. How would you interpret it? So suppose you got a pair of ones. If you reinterpret the second die as being, instead of 1, a 6, what's the sum of the two dice? Okay, how about if there were 2s? 7. 3s? Right? So you could think of this question about whether the sum of the two dice gives you 7 as a different question where you roll the two dice and then instead of taking whatever comes up on the second die, you just sort of subtract that number from 7. Right? So if it's 1, you call it 6, 2, 5, etc. You just swap these numbers around. But if you swap them around, what's the chance you'll roll a 6? Same as what it was before. What's the chance you'll get a 5? Exactly the same as before. So it doesn't change the outcomes. As probabilistically, you're rolling the dice. It doesn't make any difference whether you call 1 a 1 or 6, right? As long as you have an equal number of everything, right? So before you were saying you roll the die and you get 1 or 2 or 3 or 4 or 5 or 6, equal probability, right? Now you're saying you get 6 or 5 or 4 or 3 or 2 or 1 equal probability. It's the same thing. Right? So what that tells us is we don't really have to go through this calculation to figure this out. We could just say this transformation shows us that the two probabilities are equal. Does it make sense? Yeah? Yes? How did I get? Oh, how did we get 6 or 12? Somebody said it and I sort of accepted it. Okay, people were trying to figure out from here, from looking at this, how many of these add up to 7, right? And so I think people were slightly confused about whether, whether you would get exactly 6 or whether you'd be able to swap, right? In fact, okay, so you could either do it this way, what I said, or you could just say, okay, look, the first, okay, how many are there? Okay, so let's figure this out. Let's figure this number out. Let's cross that out. Okay, let's roll the first die. It is whatever it is. Okay. Now I claim that no matter what the first outcome is, there's exactly one outcome which gives you a sum of 7. Right? If it's 1, then 6 will get you to 7. If it's all the way to 6, then you still can go to 7 by 1. Right? So there's exactly one outcome for the second die, where the sum is 7. So the answer is exactly 6 divided by 36, and so they're equal. Okay, so there are 2 ways you can solve it, either by, 3 ways. You either enumerate, or you reason like this, or you reason like this. Yes? Okay, yeah.
Show like a more difficult example.
I'm sorry?
Show more like.
No, let me show you. This was just a special case of something. Let's move on to a more generic example. Okay? So actually, are we moving to a more generic example, or let me start first by telling you the what the definition of probability is, and then I'll give you more generic examples. Yes.
It would have taken like not that much time to do it the way you're just counting right there, right?
Right. You could do it by counting if you wanted. There are only 36 possibilities here, but soon I'll give you examples where the number of possibilities gets astronomical, which is what typically happens in probability, and that's why we do probability theory. And so then figuring out these probabilities involves, we'll do it through counting. Okay, so now let's try to formalize what went on here. So clearly, what probability is about is these sorts of sets, right? There's a set like this that we are interested in, and then what else are we interested in? What we are interested in is the probability of something like this. What's the probability that you got a pair? So what does that mean? We are interested in knowing what's the probability that we got this sort of outcome, right? So we are saying, what's the probability that you got 1, 1, or 2, 2, or 3, 3, or 6, 6? Okay? So already you see a pattern here. So when we talk about probabilities, we are saying, first of all, we do an experiment. An experiment consists of rolling 2 dice or tossing a coin many times or something like that. And then we say, we can write out all the possible outcomes. That's a set. It's a big set, often. And then what we are interested in knowing is, did some event occur? An event like this. Was it the case that after you rolled the dice, both of them came up with the same outcome? Right? Okay, so that's an event, but what does an event look like? Well, we go back and look inside the set, and we say, an event is a subset of this entire set of possible outcomes. Right? So we look at, there are all the possible outcomes that can occur with our experiment, and some of them we like, and some of them we don't like. The ones that we like, we label as the event. Right? And that's what we're saying. What's the probability that a pair occurred? What's the probability that this subset actually came up? Right? Okay, so that's how we are going to define probability theory. So first we have this notion of an experiment, which usually consists of something like this. So we have a universe U. Okay? U is a population. And then we sample from U k times, with or without replacement. Okay? So what would U be? U is a small set. U might be heads, tails, or U might be 1, 2, 3, 4, 5, 6. So in the case of a coin or die, 6-sided die, that's what U is. And then we are sampling from U many times. Okay, with or without replacement. Or it might be a set of cards, a pack of cards, and we are sampling from it to deal a poker hand. And then, okay, so let's say that U was heads, tails, and we flip the coin 3 times. Okay, so what do we get? What we get is a sample space which consists of all possible outcomes to these 3 coin flips. So there are 8 possibilities now for that sample space. So omega is our sample space, which is all possible outcomes of this sampling, right? So it might look like what we had before, heads, 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 all the way down to tails, tails, tails. It might be these 8 sample points. And then we say, so what we say is that these are, so the typical sample point we call little omega. So this is capital omega. And that's little omega for element of this sample space. And then often we'll assign probabilities to these points by saying all the points are equally likely. Right? That's what we said when we said we had a fair coin. So we might say all sample points are equally likely. And so the probability of any sample point omega is just 1 divided by the number of sample points, which in this case is 8. So it's a cardinality of this sample space. Right? And then an event, E, is just a subset of omega. So we just say, if we were interested in all those sample points where there's exactly 1 heads, so there were 3 such sample points, so our event would be that subset of those 3 sample points. And then the probability of E would just be the number of points in that event divided by the number of points in the sample space. Okay, so this is what probability theory looks like if you have, in the special case when all your sample points are equally likely. Okay, so this is a uniform probability distribution. Now, in general, that's not going to be the case. So in general, you'll have your sample space omega, okay, your sample point little omega in there, and for each sample point, there'll be a probability which is between 0 and 1. The other property we'll have is that if you sum over all the points in the sample space, the sum of their probabilities must add up to 1. So the sum over all sample points of the probability of that sample point must equal to 1. So for example, you might have a bias coin. Okay. These are actually things you can purchase, usually in a magic shop. You can purchase a coin which in which the weight is uneven, so that if you toss it, it's much more likely to come up heads than tails. And then, you know, it's this can be a useful thing if you make your money gambling, or if you want to do a trick somewhere. Right? Okay, so let's say that you have a bias coin where the probability of heads is 2/3 and the probability of tails is 1/3. Okay, so now, and let's say that you toss this coin twice. Okay, you toss it twice. So what does our sample space look like? Well, it looks, you know, of course there's tails, 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 heads, heads, tails, heads, heads. But what about their probabilities? Now their probabilities are not 1/4 each, right? 1/4 was just half times half. But now the probability of tails, tails, okay, this is something we'll, you know, I'm just going to do it right now, but later we'll justify it in a couple of lectures. So the probability of tails, tails is just 1/3 times 1/3, which is 1/9. The probability of tails, heads is 1/3 times 2/3, which is 2/9. The probability of heads, tails is also 2/3 times 1/3, which is 2/9. And the probability of heads, heads is 2/3 times 2/3, which is 4/9. Okay, so now you could say, well, what's the probability that you either get both tails or both heads? So the probability you get equal outcomes is 1/9 plus 4/9, which is 5/9. And that's this event. Is it clear? Okay, so again, let's do a recap. So what's, you know, how do we work with probability theory? We have the notion of a sample space, right? What's this sample space? Well, it's the set of all possible outcomes to our experiment. So we are performing an experiment. You know, when we perform the experiment, we get one of these outcomes. We get only one of these outcomes, right? These are all the possible outcomes we can draw from, but when we perform the experiment, we just get one of them. Okay. Now, what kinds of experiments do we perform? Usually, we perform experiments where there's some population and we draw from that population repeatedly, either with or without replacement. Okay? But there might be other experiments you can perform. The rules will still look like this. Right? And then we have some way of assigning probabilities to each of these sample points. So these are called sample points, right? The entire space is called a sample space, right? So now there are different ways you could assign probabilities to these. The easiest one is when you say they are uniform, meaning all of them have the same probability. If they all have the same probability and they all add up to 1, then each one has probability equal to 1 divided by the number of elements in the sample space. But sometimes we might not assign uniform probabilities. And then we might assign probabilities in any way such that each point has a has a non-negative probability, and the sum is exactly 1. Okay, so this, the probability of omega is just the chance that you will see it, and the sum of the probabilities just says that when you perform the experiment, something always comes up, right? There's some outcome. Okay. Okay, so let's do one more example, and then. Okay, so remember I said that in general these sample spaces are going to be very large, and so to compute the probabilities, we can't really write out the sample space the way we have been doing. So we have to be more clever about computing probabilities. So here's an example. So let's say you're playing poker, and you want to know what's the probability that you get a pair. Okay. So what's a pair? So first remember what a poker hand is. So a poker hand is you're dealt. It's a 5-card hand. So out of the 52 cards, you're dealt 5 of them at random. And then a pair means that, you know, it's something like this. So you have 5 cards. What we want is that 2 of them are the same. So for example, you might have 4 of diamonds, you might have 4 of spades, and then you have a queen of clubs, ace of diamonds, 2 of hearts. Right? So it's, you know, a pair is of this form, you know, where exactly out of the 5 cards, you know, the order doesn't matter in these cards, right? They can be in any order at all, because you've got all 5 of them. Right? So a pair is of the form where you have x, x, u, v, w, where u is not equal to v is not equal to w. In terms of denomination, of course, the suits can be anything you want. Right? You don't care about the suits. 2 of the cards are the same, so it's 4, 4, and then everything else is different, and different from this one. Not equal to x. Right? So these are all different. All 4 are distinct. Okay, so what's the probability of a pair? Well, you know, in principle, you could say this. Well, you have the sample space, and then within that you have all possible pairs, and all you need to do is you need to figure out what's the cardinality of this set of pairs divided by the cardinality of omega. Okay? And so we could just write out laboriously all the points in the sample space, figure out which of them were pairs, and then we'd have the answer. The problem is the number of points in this sample space is astronomical. It's really large, right? Because the cardinality of omega is what? Yeah, it's 52 choose 5, which is what? It's 52 factorial divided by 5 factorial, 47 factorial, right? Which is what? Okay, so it's 52 factorial is 52 times 51 times 50 times 49 times 48. Okay, this will take a long time, so let's just write it as 47 factorial divided by 5 times 2 times 5 times 4 times 3 times 2 times 1 times 47 factorial. And so you can cancel those. Okay, so it's the top 5 terms divided by 5 factorial, right? Okay, but that's still a large number. That's a very large number. Okay, so we don't want to write out all these possible hands. So what we want to do is we want to figure out what's the cardinality of number of pairs. Right? So how do we do it? How do we figure out the number of pairs? Okay, so what we're going to do is we're just going to apply the first rule of counting and the second rule of counting and the first rule of counting and the second rule of counting until it's done. Okay, so what do we do? Okay, so to have a pair, what must you do? You must pick something. So what do you pick? You pick which one, what the denomination of the card is, which will be a pair, right? So to pick out this hand, one way of picking it out is you decide how many ways are there to pick which one is a pair. Is it 4 or 3 or 2 or ace? Right? How many ways are there of doing that? How many possible choices are there for which pair do we have? 13. And then, given that we picked that out, how many ways are there of picking the 2 cards? Okay, so no matter which one we picked, so we are using now the first rule of counting, no matter which one we picked, so whether we picked 4 or 3, or whichever one, there are exactly 4 to choose 2 ways of picking the exact 2 cards, right? So it's times 4 choose 2. Okay, so now we are done with that, and now we have to pick the remaining cards. So now we say, no matter how we pick these, how many ways are there of picking the next card? Okay, so how many ways are there of picking the... I'm sorry? A 3 of a kind is not a pair. So I'm counting exactly 2 of a kind. So what I want is, so remember I specified what I want is that all x, u, v, w are all distinct. So what I mean is, they're all distinct. Right? So all pairs of these are distinct. Yeah? Okay. So now how many ways are there of picking the remaining cards? So what rule of counting should we use? The first rule. Okay, and now, okay, so what do we want to do? I'm sorry? We have 12 to choose from. We want to choose 3, right? We already chose 1. I'm sorry? They all have to be different.
So now you have 12 different numbers to choose from, but you can only choose 1, and then after that 11 more that you can only choose 1.
Yeah, so you could, you're right. So you could either say choose them one at a time, or you could just say you have 12 numbers to choose from. You want to choose 3 of them, right? So how many ways are there of choosing 3 out of a set of 12? 12 choose 3. So let's do 12 choose 3. So let's say we've selected those 3. They happen to be queen, ace, and 2. But now we still have to choose the cards. So how many ways are there of choosing the cards? 4 for each of them, right? So each of them, for the queen, we have to choose what its suit is, and there are 4 possibilities. For the ace, we have to choose a suit. There are 4 possibilities. So it's 4 to the 3. Okay, so that's the number of pairs. Right? And so you divide. So the probability that you get pair is 13 times 4 choose 2 times 12 choose 3 times 4 cubed divided by 52 choose 5. Yes? Why did we get 4 to the 3 here? So remember what we did? We started by picking out the first 2 cards, right? They don't. It doesn't matter which order. We are just picking a set. But we said which one is the pair, right? So let's pick out the pair. That happened to be 4, right? We just picked it. It was 1 out of 13 possibilities. Then we picked the 2 cards. We said, okay, we are done with that. Now we need to pick 3 other cards. But they can't be a 4 again. We can't pick that same card again. So we only have 12 possibilities left. But out of those, we pick 3 cards, 3 denominations, right? So that's 12 choose 3. But we haven't picked the cards yet. We've just picked the denominations. So we just said, well, it's got to be a queen, an ace, and a 2. But now we've got to pick out the suit of that denomination. So for each of those cards, what we need to specify is which suit. But there are 4 possibilities for each of them. So there are 4 possibilities for the first. No matter what we pick, there are 4 possibilities for the second. No matter what we pick, there are 4 possibilities for the third. So that's how you, yeah, yes.
Why did you divide the 52?
I'm sorry?
Why did you divide
Why did I divide by 52, choose 5? Because that's all possible poker hands. Right? That's our sample space. So the probability is you look at the size of the set divided by the size of the sample space. Yes? Yes. Okay, good question. So there are other ways of doing it, but there was a question here, of a particular way of doing it. So let's say that we finished choosing these first two cards. Now we are left with 48 cards we can choose from. Couldn't we replace this by 48, choose 3? I'm sorry? No, see, because if you replace it by 48, choose 3, then you're just picking 3 cards out of the remaining 48. But those 3 cards might be, for example, you might pick an ace, and an ace. And that's not right, because you need to pick cards of different denomination. Right? So, but you could do it differently. You could sort of say, well, there are 48 ways of picking the next card. Certainly. Right? Because any of those 48 is going to be fine. But once you pick it, how many ways are there of picking the next card? 44. And then once you pick that, how many ways are there of picking the next card? 42, right? 40, right? So you're right, 40. Right? So basically, what do? You pick these cards. Now you've eliminated 4 cards from the deck. Then you pick the next one. So you pick 1 out of those 48 remaining cards, and then once you pick it, you eliminate that card and 3 more cards, the other 3 cards of that denomination. So you're left with 44. You pick 1 of those, and then you eliminate that and 3 more. So you're left with 40. So the other way you could have written it is 13 times 4 choose 2 times 48 times 44 times 40. Right? So there are many, many ways of working it out. All you have to do is make sure you're using the first rule or the second rule. Yeah? Just make sure, no matter what you picked, there are still this many ways of doing it. Right? It's the no matter that gives you the right to multiply. Yeah.
I think if you do 48 times 44 times 40, you have to divide by 3 factorial.
Or you have to divide by 3 factorial. Good. That's right. Yes, so you have to use the second rule again, right? Because very good point. So let me go over this properly, because it's important that you understand this, right? So the point was, suppose we say that we are going to pick this next card. It's 1 out of 48, and then the one after that it's 1 out of 44. Next one is 1 out of 40, right? Now we have to say, but we could have picked those cards in any order, right? Because when we said there are 48 ways of picking the next one, we are including the queen of clubs and the ace of diamonds and the 2 of hearts. These will be 3 different possibilities out of those 48. So let's say we pick queen of hearts. The next one, again, we have 44 possibilities. We might pick 2 of hearts, right? And then we might pick ace of diamonds. But it's the same thing as if we picked queen of clubs and then ace of diamonds and then 2 of hearts. So we have to divide by the number of different ways we could have picked that, and that's 3 factorial. So we'd have to divide by 3 factorial, which is this one. Right? Okay, here's a question for you. How come we did not have to, how come we could just place this first without saying, well, divide also by something factorial, because what gave us the right to pick this pair first? Why could we say, well, there are 13 ways of picking the first card, the pair, 4 choose 2 ways of picking those 2, but then we never had to say, well, we can interchange that with the rest of the cards. Why did we not have to do that? Why did we have to do that here? If we said 48 times 40 times 44 times 40, why did we have to divide by 3 factorial but not by something factorial here for this first piece. Yeah.
4 choose 2 is independent order, so when you're counting 4 choose 2, say spades and diamonds, equivalent to diamonds and spades.
Good. So there are two kinds of orderings we might worry about. One is the order of the two of the pair, whether it was diamonds, spades, or spades, diamonds. That we took care of in this 4 choose 2. The other kind of ordering we might wish to worry about is what if those 4s occurred later or at first? Right? How come we didn't count them differently? Well, what we did was we said, let's look at this poker hand, right? If it has a pair in it, it has exactly one pair in it, right? Then we may as well move that pair to the front. Now we are going to count it only once. You see what we did? Right? So since, we are saying we are going to count this only once because we are moving it all the way to the front, and then the pair occurs in a particular place. Right? That's where we already took care of the fact that we don't mix things up. Okay, so that was our counting rules. Okay? Okay. How about a 2-minute break and then we'll continue.
Just explain to me again really quickly the 4Q. I understand the rest of it.
The 4Q?
Yeah.
That's just the suit. Is it spades or hearts or clubs, diamonds?
Okay. Okay. Awesome. Thank you.
Divided by the 3 factorial in the other case?
Oh, because those 3 cards,
Yeah.
they could be in any order.
Okay.
We overcounted
So
by 3.
48 times 44 times 40 over 3 factorial.
Yeah.
Okay. How would we do that in more formal?
Or you just say, well, there are that many choices. If you choose that many times, you get an ordered object. You get them in a particular order.
So you count them as one set.
You get the sequence, and then you want to get the set. You say how many ordered sequences are there per set, right? Remember the second rule of counting? So we apply the second rule of counting. Try shouting. Okay.
Why can't I do 13 choose 4 instead of the 13 choose 1 and then 12 choose 4?
You're right. You could do 13 choose 4. Well, you could do 13 choose 4, but then you'll have to do 4 choose 1 to get the one that you're going to. You'd have to do 4 choose 1 then to say which one are you going to make into a pair.
Why didn't we have to divide by another factorial at the end? Because we didn't care about the order of the 5.
That's right. Sorry?
So like at the end, so when we got that whole expression, those four terms,
Yeah.
why don't we have to divide by 5 factorial because we don't care about the order?
Because we already made sure we don't care about the order.
Okay. From the very beginning?
Yes. Okay. So maybe let me clarify this point again. Okay. All right. So let's spend a little more time on this because you know I think it'll it seems like most of you understand it, but if I spend a little more time, maybe you'll understand it even better. Yeah. Okay. So there are a few. There was a question that came up, which is sort of what I was getting at before, which is, you know, since we do not care what the order of those cards is up there, right? We don't care. It's just a hand of cards. You know, you can rearrange them as you want. It's your hand of cards, right? So we don't care what the order is. Why don't we then divide everything by 5 factorial after doing all this? Okay. So, yes? Yeah, so somehow, the answer is somehow we already took care of that. We already divided by whatever we needed to divide by. And dividing by 5 factorial was not the right answer. Okay, so let's look at this example again in a couple of different ways so that you can convince yourself that, you know, remember the rules of counting are very simple, but they're also pretty specific about what you have to do, right? The first rule says you have a right to multiply the number of possibilities, but you only have that right if no matter what you choose the first time, there are this many possibilities for the second, and no matter what you choose the first so many times, there are exactly the same number of possibilities for the next choice. That's what the first rule of counting says. It's simple, but it can only be applied when this condition is satisfied. The second rule of counting is also equally simple. It says, you know what it says. It says you're counting the number of sheep. You had better be sure that all the sheep have exactly the same number of legs. If one of them was lame, you can't apply the second rule of counting, right? So better make sure your sheep are completely uniform, and then you can apply the second rule of counting, right? Okay, so somehow that's what, you don't divide by 5 factorial because your sheep don't have the same number of legs here, okay? Because, there are 2 fours, you have a pair, and pairs act differently from so if you were to rearrange the first 4 and the second 4, you get the same thing again, right? So you shouldn't be dividing by 5 factorial because some of those rearrangements give you back the same thing. So it's the wrong thing to do, right? So we had better make sure that we find a way of, so what we are looking for is a clever way of arranging the counting so that we can apply the first rule and the second rule, first rule, second rule, etc., until we are done, right? So, okay, so let's go back and figure this out. I'm going to solve this problem twice. I mean, there are many different ways you can compute this answer. Okay, there are many correct ways of doing it. There are also many, many incorrect ways of doing it. Okay, so let's go over 2 correct ways of doing it, and then, incorrect ways, they're much easier to find, so I won't bother. Okay, so let's see. What do we want to do? So, okay, so we had, we had this. I don't know what we had, but let's say 4 of diamonds, 4 of hearts, 2 of clubs, ace of diamonds, queen of hearts. Okay, so these were 5 cards, but we could have got them in any order, right? But what we know is that we have a pair in there, and that everything, there are 4 different types of cards. There are 4 different denominations. Now I claim that the way you can write the set of 5 cards, so it's a set, not a sequence, it's a set. They can occur in any order. But I claim that you can uniquely write them in this order, because just by looking at them, you know which is the pair, right? There's only one of them. So you write out 4 4. That's the pair, right? 4 diamonds, 4 hearts. And then you also have a set of cards where it's 2 ace queen of whatever, right? Yes. So what I'm saying is, you can assume without loss of generality that you know which is the pair and which is the not pair, right? You can reorder them so that the pair always occurs first. That's what gives you a right to say, let me first choose which one is going to be the pair. Now I don't have to reorder anything because that the 4 is occurring first. That's the pair, right? Once I pick it, I know this is what's going to be replicated twice. There's no reordering of it ever that's going to come up. So that's why we said of the 13 different denominations, we first choose one. Right? And then once we choose it, we have to choose 2 copies. So having chosen it, that's the number of ways of choosing the 2 copies. And then we pick this set. So how many ways are there of choosing it? There are only 12 cards left. We picked one denomination. So now, for this, there are only 12 denominations left. So you choose 12, choose 3. Yes? Now, we've already accounted for order here, right? Because when we say 12, choose 3, we picked out the 2 ace and queen, but we didn't say in which order because we are choosing a set. So we don't need to divide by anything again, right? We chose them as sets, right? And then we said, now let's assign a suit to each one, and suits there are 4 to the 3rd. So is it clear that the thinking that went behind this is we were already picking them as sets, and we said the fact that you can say that there's one set and a second set comes from the fact that the pair is playing a different role than the singletons. And you can identify them, so you may as well pick them separately. So that's one way of calculating this. Now here's another way of calculating it. Okay, so you might say, well, first let me pick the first card of the pair. How many ways are there of doing that? 52. Having picked that, how many ways are there of picking the second card of the pair? I'm sorry? And now, since I've picked the 2 cards, have I picked them as a set or have I ordered them? They're ordered, right? So I'd better divide by 2. Yes? Yes? Sorry, there was a question. So I picked the first card out of the pair, right? There were 52 ways of doing it, but having picked it, so suppose it turns out, the first card of the pair happened to be the 4 of diamonds. Now I know the second card, since it's it's part of a pair, the second card's also going to be a 4. But the 4 of diamonds is already used up, so there are only 3 4s left. So there are only 3 possibilities for the second choice. But now, also, I could have picked them in either order, so I have to divide by 2. So that is exactly 13 choose 1 times 4 choose 2. And then, having done this, then I say, well, to pick the next card, now there are 48 possibilities. So we go ahead and pick that. For the next card, there are 44 possibilities. For the next card, there are 40 possibilities, except that I picked them in order. Right? So I picked the 2 of clubs, and then the ace of diamonds, and then the queen of hearts. Except if I'd picked them in the opposite order, if I'd picked the queen of hearts and then the ace of diamonds and the 2 of clubs, I'd have counted it as a separate, as a separate possibility in this 48 times 44 times 40. So I have to divide by all these possibilities, all the possible orderings. But how many orderings are there? So this is the number of legs of the sheep, right? So how many legs does this particular kind of sheep have? Well, it's 3 factorial, right? So I have to divide by 3 factorial. And this is exactly 12 choose 3 times 4 cubed. Okay, so there are many different ways you can calculate this. All you have to do is make sure that the conditions of the first rule and the second rule apply when you're applying those rules. Make sense? Yes.
Can you explain a little bit again why it's 50 times 3 over 2, but why the over 2?
Okay, so what was this 52 times 3 over 2? So there were 52 ways of choosing the first card. Right? We already said that the first 2 cards are the pair, right? Because of that way of ordering things. Okay, so 52 ways of choosing the first card. Now, when we pick that card, we know the denomination of the second card. So now there are only 4 cards of that denomination, but we already picked one of them. So there are only 3 cards left to pick from. So it's 52 times 3. But now, let's say we picked hearts first and then spades. Okay, we could also have picked spades and then hearts. But those are the same thing because we are picking them as a set. So we overcounted by a factor of 2.
So it's almost like 2 factorial.
Yeah, it's 2 factorial, exactly. So, yeah, yes.
So why did you multiply by 48 there? Because I thought after you pick the first 2 cards, it's supposed to be cards on each deck.
You have 50 cards, but 2 of them are of the same denomination as the pair. Right? So if we pick 4 of diamonds and 4 of hearts, now there's still a 4 of spades and a 4 of clubs left over. But we are not allowed to pick them again because we want to pick a card of a different denomination. So we throw them out. Right? So we have only 48 cards left to pick from. Okay, so everyone happy? Okay. So, okay, so I went a lot slower than I expected, but I'm actually happy to do that because it's sort of more important that you get this once. You know, if you get this once, then it's smooth sailing from here. So, okay. So now, let me just think. Of the remaining examples I was going to do, which one would be most useful? Let's do another example sort of this kind, and then if there's time, we'll do one more. Yeah. Okay. So this is a problem of sort of, you know, it's called load balancing, hashing. You know, so let's say that you have n bins. And you have m balls. And so they're numbered 1 through m. And you want to place these m balls in the n bins, okay, at random. So first let's figure out what's omega. What's the cardinality of omega? Okay, think about it for a minute. Yeah, you know, these things, unless you think about them for a minute, they look difficult. If you think about them for a minute, they become easy. So please take a minute. Sorry, did you want to answer, or did you have a question? Yeah. Yes. Yes. Sorry. Let me just say, until we get to quantum mechanics, balls are always distinguishable, right? So, actually, if you want to know, you know, what is why are anything classical is distinguishable? Because you can follow it around. Measuring it doesn't do anything, right? So, it's always distinguishable because, you know, you could just be looking at it all the time, and so you could say, well, that was the first one, that was the second one. You don't have to actually be able to tell them apart. You just have to follow them everywhere, right? And they're always distinguishable. In quantum mechanics, you can't follow things around because as soon as you look at them, it changes them. And so, you know, and that's why this whole question comes up, are they distinguishable, are they not? Yeah? Yes?
Can you repeat one more time what you mean by order of arrangement?
Order of what?
What that means?
Oh, what's that funny symbol up there? You know, first of all, that funny symbol within those two vertical lines is a capital omega. That denotes the sample space, which is a set of all possible sample points. And then when you put any funny symbol inside these parallel lines, that usually denotes cardinality of, which means the number of, the actual size of the set, or the number of points inside that set. Okay, so back to the cardinality of omega. Well, there are exactly n ways you can place the first ball. No matter how you place it, there are exactly n ways of placing the second one, so on. So it's going to be just n raised to the power of m. Okay. Now, what's the event that we are interested in? The event that we are interested in is, what's the probability that the first bin is empty? Okay, so let's let E be this event. Does everyone know what I mean by saying E is the event that the first bin is empty? It's all possible sample points where the first bin was empty. Right? So there are n to the m ways of placing these m balls in the n bins. Out of these, there are many ways in which no ball got placed in the first bin. So look at the set of only those sample points. So we'll call that set of sample points E. So E is a subset of omega. And what we want to know is, what's the cardinality of E? So what is the cardinality of E? Yeah, good. So this is n minus 1 to the m. Right? Because you're excluding the first bin. The first bin is empty. So each ball you get to place in only bins 2 through n. So it's as though n got replaced by n minus 1, and you're back to the same question. So it's n minus 1 by n. So what's the probability first bin is empty? It's the cardinality of E divided by cardinality of omega, which is what? N minus 1 to the m divided by n to the m, which is what? 1 minus 1 over n whole raised to the power of m. Okay. Now, okay, so that's the probability that the first bin is empty. Now, yes.
For cardinal value of omega, since it could be like in say 1, there could be 0 to m. Doesn't that mean it's m plus 1 possibility?
Sorry, in which one?
For the cardinal value of omega.
Yeah. So what's
Each box has m possibilities.
No. Sorry. Okay. So let's go over how did we figure out the cardinality of omega? How did we figure out the number of sample points? So we said, how many ways are there of placing the m balls in the n bins? So we start with the first ball, and we say, where can we place it? Anywhere we want, right? There are n possibilities. So there are n ways of placing the first ball. Now, no matter where we placed it, how many ways are there of placing the second ball? N. No matter how we place the first two balls, how many ways are there of placing the third ball? N. So it's n times n times n times n, m times. So that's n to the n. Yeah? Okay, so this is the important thing. You know, we are never going to be doing anything difficult, right? So, well, we might be, but all the steps will be simple, right? So if you ever find yourself making a step which you don't understand, you're not doing the right thing, right? Every step is going to be like this. It's going to be saying, no matter what we did before, there are this many possibilities, so you multiply them. Or we are counting sheep. You know, every sheep has exactly this many legs, so divide by that much, right? So that's all we are going to be doing. Okay, now let me just let me just say how this number grows. Okay, we won't prove it, but let me tell you how it grows. So for example, if n equal to 20, m equal to 20, right? This is 1 minus 1 over 20 whole raised to the power of 20. So you have 20 balls, you're putting them into 20 bins. What's the chance that the first bin is empty? Well, it's 1 minus 1 over 20 to the 20. What's that equal to? Okay, this is approximately 1 over e. Very good. In fact, not only is it approximately equal to 1 over e, it's almost exactly equal to 1 over e. Okay. This is true for all n. 1 minus 1 over n to the n, it converges towards 1 over e. And it converges very, very quickly. So even for relatively small values of n, it's about 1 over e. So you remember what e is? E is 2.71 something? 2.7? Oh, okay. What he said. Okay. That's what e is. What's 1 over e? What's 1 over e? It's about 0.34 or something. Let's say it's 0.34. Okay. Nobody knows, so I'll just put it down. Okay. Now, what if what if you were putting you had n equal to 10 and m equal to 20? How would you figure this out now? Well, you would say, look, 1 minus 1 over 10 raised to the power 20 is 1 minus 1 over 10 raised to the power 10, whole thing squared. Right? That's what if you're raising it to the power 20, you may as well raise it to the power 10 and then multiply it by itself. But 1 minus 1 over 10 to the 10, we said, this is always, this approaches 1 over e so quickly that even for 10, it's very, very close. So this is about 1 over e squared. Okay, so it's 0.34 times 0.34, which is about 0.13 or something like that. Okay, so that's what. So basically, the chance that you see one empty bin if you put n balls in n bins is about whatever, 34%. If you're putting twice as many balls, it becomes 13%. It goes down very rapidly from there. Yes? One last question. So suppose we wanted to figure out what's the probability that the first bin is not empty. What would that be? Yeah, so remember we have this, if this is omega, we have an event E. So E might be the event first bin empty. Then the complement of E is the event the first bin is non-empty. And what we know is that the probability of omega is 1, is the probability of E plus the probability of E complement, right? Because every sample point is either an E or an E complement, right? So the probability of E complement is just 1 minus probability of E. So, right? So the probability that the first bin is non-empty is just 1 minus the probability that it's empty. So if there was a 34% chance that it was empty, then there's you can do the math, right? 66% chance it's not empty. Okay, so let's, let me, I'll just tell you about the next problem. It's something you should think about, and then we'll talk about it the next time. Okay, so So this is what's called the Monty Hall paradox. So the story is this. Back in the 60s, there was a game show on TV called Let's Make a Deal. And the host of this game show was Monty Hall. And the way he'd play this game is that there were 3 doors. And behind one of these 3 doors at random, they'd place a prize, like a car. Okay, so there was a car behind one of these doors. Okay, but the rest of it I can't draw because I'm not very good at drawing. So, okay, so behind the other 2 doors, behind each of the other 2 doors, you place a goat. Okay, so I don't know. This is not very good, but okay. Now the contestant was allowed to choose which door to pick. So at the beginning of the show, the contestant would pick one of these doors. Let's say that one. Okay? And then, after that, the fun would start, and Monty Hall would sort of try to make deals with this person to say, well, do you want this, do you really want to open this door, or do you want something else, and so on, and they'd keep trying to make deals. And then at some point, Monty Hall would sort of say, well, he had an assistant, right, who would go and open one of the other 2 doors. But the assistant never picked the door behind which the prize was, right? Because no matter whether the prize was behind this door or not, since there are 2 other doors, there's definitely one of these doors behind which there's a goat. So the assistant would pick one of the doors that the contestant did not pick, but one behind which there was a goat, and would open that door and then Monty would say to this contestant, do you want to switch your mind? Do you want to change your mind? Okay? So the question is, if the contestant got this far, what's the right response? Change or not? Switch or not? Oh my God. I'm sorry? Good question. Okay. Okay, so that's the question, and we'll talk about it next time.